Alright guys, Mr. B here. This video is going over the answers to the questions in the 8.3 notes. So if you're confused on any of them, hopefully this will help you. Okay, looking at number 1, it says classify as always true, sometimes true, or never true. A 3-atom molecule is bent. So that answer is going to be sometimes true. And here's how I can show you that that is always sometimes true. So we're going to draw 2 molecules here. One of them is going to be CO2, and the other one will be H2O. Now in this video, we're not going to be going over specifically how I'm drawing these, so if you have questions on that, there's other videos for that, but I'm just going to draw these out. So CO2 is going to look something like this. We have our carbon in the middle, and we have 2 double bonded oxygens at the outside. And H2O is going to look something like this. You know what, I'm just going to draw them both straight across, even though geometry-wise they would look different. Okay, so both of these are 3 atoms, okay? So this one here is 1 carbon, and then we have 2 oxygens, so that would be 3 atoms. And then this one here has 2 hydrogens and 1 oxygen, so also 3 atoms, okay? So both of these are 3 atoms, however, they're not both bent. One of them is. Okay, this one is a bent molecule, and this one is a linear molecule. Now you might want to be asking, of course, well, how do you know that? All right, so I'm going to go look back at the notes here. So there's some steps that can tell us how to determine the molecular geometry. First step was to write the Lewis structure, which we've done already. Okay, we have both Lewis structures written here. We're going to count the number of electron domains around the central atom, and that is any single bond, a double bond, triple bond, or any lone pairs. Okay, so looking at the CO2, the carbon is in the middle, so this is 1 electron domain, and this double bond is a 2nd electron domain, and we don't have any lone pairs. So this would give us a total of 2, I'm just going to write ED for electron domains. Whereas in the water, we've got 1 bond, that's 1, 2 bonds, that's 2, lone pair, that's 3, and another lone pair, that's 4. So this has 4 electron domains, okay, the water does. So once we've counted electron domains, there's this chart here. This will tell us our VSEPR geometry or our electron geometry, which we're going to skip past that for now because what we care about is looking at this part, the molecular geometry. So using this chart, we're going to determine what the shape is of each of these, okay? So again, looking back at our pictures, this CO2 had 2 electron domains. So looking back at our chart, we have total number of electron domains is 2. How many non-bonding or lone pairs that are on the central atom? Looking back at our picture, we have 0 lone pairs on the central carbon. So using this chart, we have 2 electron domains, 0 lone pairs. That gives us a linear molecule. Whereas for water, H2O, we had 4 electron domains. And looking at the oxygen, there are 2 lone pairs on the central atom. So we have 4 electron domains, 2 lone pairs. That gives us a bent shape. Okay, so that's how I know that the answer to that question is only sometimes true, because these both have 3 atoms in them, but only one of them is bent, the other one is linear. All right, number 2, predict the shape of the compound carbon tetrafluoride, CF4. Okay, so to do that, we're going to want to draw it out first. So let's draw it real quickly. Again, this is not going to go over how I know this, what this looks like, so I'm just going to draw it. Okay, so we have carbon in the middle, 4 Fs around it. If you want to, we can put the lone pairs on all the fluorines. We don't really need to because when we're trying to find the shape of the molecule, the outside atoms with the lone pairs don't really matter. Only the lone pairs on the central atom matter. But either way, here's what it looks like. So if we count electron domains, we have 1, 2, 3, 4. Okay, so 4 electron domains. Going back to our notes, let's use our chart here. 4 electron domains. Number of lone pairs on the central atom, just to double check one more time, we have 0 lone pairs on that carbon, so that's 0. So total number of electron domains is 4. 0 lone pairs on the central atom. That gives us a tetrahedral shape. So for this one, number 2, this would be tetrahedral. Okay. Number 3, predict the shape for phosphorus trifluoride, PF3. Okay, so again, we'll draw it out. Let's get a new piece of paper here. Again, I'm not going to go over how I draw it. I'm just going to simply draw it. So PF3 would look something like this. We do have a lone pair on the phosphorus in the center. We'll put the lone pairs on the fluorines, even though, again, they're not really going to do anything or determine any shape. So here's our PF3. Let's count electron domains. So 1, 2, 3, 4. Lone pair counts as well. So that's 4 electron domains. Okay, so 4 electron domains. We have 1 lone pair on the phosphorus. Let's take a look at our chart here. 4 electron domains, 1 lone pair. That gives us a trigonal pyramidal shape. Okay, so this one here would be trigonal pyramidal. Okay, moving on to number 4. Predict the shape of BCl3. Okay, so to do that again, we're going to want to draw it. So BCl3 is going to look like this. Now, this is a weird molecule in the fact that we are not satisfying the octet rule on the boron. Okay, so if we count the total number of electrons on the boron, we actually only have 6. 2, 4, 6, which usually we want to have 8. Boron is one of those elements that just is fine with having 6. So anyway, this is our molecule. If we count electron domains, we have 1, 2, 3. 3 bonds, so 3 electron domains. There are 0 lone pairs on the central boron. So let's go back to our chart. We have 3 electron domains, 0 lone pairs on the central boron. This will give us a trigonal planar shape. So this would be trigonal planar. Okay, and the last one here is predict the shape of fluorine monoxide. So this is F2O. So again, let's draw this out. It's going to look something like this. And on the oxygen, there will be 2 lone pairs. Again, I'm not going over how I'm drawing this out. So if you have questions on how to draw this, there's other videos for that. I'm just drawing it out. All right, so here's our shape of our molecule. If we count electron domains, we have 1, 2, 3, 4. Okay, each bond counts and the 2 lone pairs each count. That is 4 electron domains with 2 lone pairs on the central oxygen. So again, let's go look at our chart. 4 electron domains, 2 lone pairs on the central oxygen. That gives us a bent shape. So this one here is going to be bent. All right. So hopefully that helps you there. But if you have any other questions, there are other videos too that go over drawing molecules and determining their shape. So, all right. I'll see you in the next video.